Oh, that captured already. Hi, everybody. Welcome to the final review. Let me just turn this down. I could listen to that forever. Like, literally forever. If they played that in, like, the afterlife, I would be fine. Most people would go crazy, but I would be fine. So I have this on the screen, just because I was trying to preload some of the stuff that students were asking for. So we'll come to this in a second, but I did want to comment on, for anybody who watches these videos later, if you are watching it the day it's posted, which is Tuesday on the 7th, Canvas is down right now. I suspect that it has to do something with the outage at Amazon Cloud Services or something like that I heard about. I don't know. I browse the internet and random things make their way to me, I guess, and I heard about this and I was like, oh. And then I heard Canvas was down and I'm like, I bet the two are connected. So hopefully if Amazon is the one working on the repairs and stuff, this will all be fixed tomorrow, and so we can have our final exam. I don't know at this time when things will be fixed. Let me just check my email really quickly to see if there has been any update. Because I've been trying to play with Canvas today, and I did click on, like, the gradebook, and it opened after, like, 2 minutes. So, yeah, if you're trying to do your final exam and it's taking that long to, like, load a question, like, that's not going to work. So, we can't do that. So, it needs to be working in its entirety before we can do that. And I don't have anything in my email. So, no updates just yet. So, we'll operate on the assumption that it will be fixed. And if it's not later tonight, I will post in the Discord some information about what we will do. Okay, so check the Discord because I can't actually send an email to the class because Canvas is down. So I have no way to communicate with you other than through this video and Canvas. So please make sure, or not Canvas, I'm sorry, Discord. So please make sure that you are reading the messages in that channel. Okay, well, let's go ahead and get started here. I do need to get my tablet, which is over here. And clean all the cat hair off my desk because the cats are cats. My cats don't like me to brush them, like, they're weird. I try to anyway, so, like, if they're asleep, I'll just, like, sneak over and brush them. Just to get some of the cat hair off. And then they're like, oh, this feels great, and then they walk away. Because that's what cats do, is they're obnoxious. So, okay, so this is Unit 7. And I want problem 6, and I want it on the screen there. So, I have the answer key. This is the answer key that was posted to Canvas for you. We don't actually need the answer on the screen. We could just have the problem here. And so the problem states, the average atomic mass of carbon is that, 12.011. Considering only two of its most abundant isotopes, carbon 12 and carbon 13, calculate their natural abundance if their isotopic masses are as follows. So, if you remember how to calculate the weighted average... Oh, I had to make something in Photoshop for a professional development thing, so all my settings are all screwed up, so I gotta fix this real quick. By settings, really what I mean is the colors for my ink were not black and some other color that you can see. So, do I have what I made? I could show you. Let's see. I think it's this, yeah? Could not open your document because it is invalid. Great. I moved it after I made it. So I don't have it. I made a little banner for Chem 140. And it has like a little flask on it. It looked nice. I'm in a professional development thing where we're revamping the class. Trying to come up with new things that students will use. I mean, I'm paid to do it, so that's cool. Oops. All right, so For the weighted average for a bunch of isotopes, remember that we need the mass of the isotopes, and I'm going to just go X. And then I need the percentage of how much X there is. And then the mass of how much of whatever Y is times the percentage of however much Y is. And so on and so on and so forth. Until you've listed all the isotopes. Well, we only have 2 here. So if I was to replace these terms for carbon-12 and carbon-13, it would be something like this. So the weighted average, which for carbon-12 would be 12.01, or I'm sorry, for carbon would be 12.011 AMU. And that would be, the first one would be for carbon-12. And the second one would be for carbon-13. And so that'd be something like this. Whatever the mass of carbon-12 is times the percentage of carbon-12. Plus whatever the mass of carbon-13 is times the percentage of carbon-13. And then we have another equation that relates the percentages together, because if I were to add all the percentages together, I have to get 100%, right? That should be a 0. Let me rewrite that. So using this system of equations, I should be able to solve for the percentage of carbon-12 and the percentage of carbon-13, because I know what the mass of carbon-12 is, and I know what the mass of carbon-13 is. And I also know what the average mass is, which I'm just going to call here M average, because I like to do algebra without writing in numbers. All right. As a bit of simplicity, so I don't have to write %12 over and over and over again, I'm going to call %12 X. And then I'm going to call %13 Y. And I'll note that over here. %12 is X, %13 is Y. And so now I just have this system of equations that I have to solve for X and Y. Well, the first step to do that is I need to substitute something for X or something for Y. So I'm going to say, okay, this is equation 1. This is equation 2. I'm going to take equation 2. I'm just going to do this. There you go. So I can solve for Y. Y is just 1 minus X. That checks out, right? Because 100% minus whatever percent X is would be Y%. And then we'll substitute equation 2 into equation 1. Right? That's like the whole thing about chemistry, is that conceptually chemistry isn't that bad. It's when we get to all the freaking algebra, right? And algebra is like the first thing we learn. And yet it's so hard. Everybody fucks up the algebra, right? Like, this is even true when you get to calculus. This is just a bizarre feature about algebra, is that it's like convoluted and stupid. It's actually very not stupid, but to me, a person that like finds algebra extremely difficult, it's stupid. Calculus makes sense to me. But algebra is like the fundamental stuff, and so you can't forget your fundamentals. I mean, I've done so much algebra that I don't have any problem with it anymore, but I totally understand that sentiment. So we're going to substitute equation 2 into equation 1. So that's going to look like this. So the average mass will equal the mass of carbon-12. That doesn't really look like a 12. Let me fix that. Times the percent of 12, which was X, plus the mass of carbon-13 times Y, which we are substituting. So there we go. Yeah, I feel you there. Sometimes you don't know if it's a math problem or a chemistry problem. And you kind of just have to gain an intuition and do a lot of problems to be able to figure those things out. Chemistry is very strange because there's a lot of conceptual stuff, but there's a lot of math too. And so you got to be really good at both. All right, we're going to solve this equation for x. And the way that I do that is I'm going to multiply out these terms to get x's out of the parentheses there. So m average is m12 times x plus m13 times 1 is 1. M13 times 1 is m13 minus m13 times x is just that. Now I'm going to collect all the terms that don't have x in it and throw them on the left side, and everything that has x will be on the right side, so we can factor it out later. So m average minus m13 equals m12 times x minus m13 times x. And so now we can factor out the x, right? We're just undoing the step that we did up here, more or less. So this next step becomes m average minus m13 equals x parentheses m12 minus m13. And then finally we just move this over. Divide by that stuff, and x is all by itself. There you go. I'm just double checking my algebra to make sure I did everything right. That looks good. All right, so now let's go fill in all these numbers. So the average mass is listed in the problem up at the top there as 12.011 AMU. And we're going to subtract carbon-13, and carbon-13's mass is 13.0033. Now you might be looking at that and saying, wait, that's a negative number. I'm going to get a negative mass. Well, don't worry, because on the bottom you're going to get a negative 2. And then they'll cancel out, and it'll be okay. Then we have just carbon-12's mass minus carbon-13's mass. So you can't cancel these numbers. Don't do that. Be careful. Can't cancel two numbers when you're doing subtraction. But what we can do is we can say, okay, well, my answer goes to the thousands place here. So this is going to go to the thousands place. So I'm going to keep 3 decimal places when I subtract. 12.011 minus 13.0033. And I get, for the top number, negative 0.992. And that's 3 decimal places for our subtraction. These bottom numbers both go to 4. So I'm going to keep all the digits. And so when I do this, I get negative 1.0033 AMU. And those cancel out. These negatives cancel out and become positive. And so our answer will be positive, which is good, because that's what we want. And then our answer should have 3 sig figs. So 0.992 divided by 1.0033. And I get 0.989 if I round. And that's x. Now, if y is 1 minus x, then I just do 1 minus that number. And that gives me 0.011. So that's Y. And we said that X was the percentage of carbon-12. And we said that Y was the percentage of carbon-13. And there you go. And so that should be what Samita got when she did the worksheet. And there you go. Now, she has more sig figs because she may have done it in a different direction. Like, if you label X as the other thing, for example, X was carbon-13 and Y was carbon-12, you actually get a different number of sig figs. So, just be mindful of that. Now, on the worksheet, you can actually see her work here. We're going to do another one of these, so we're going to come back. Oops. I don't know where her work is. I was just looking. There it is. And you can see that she did all of these steps to get these answers. Now, it looks like Samita doesn't do algebra by manipulating the symbols. She just writes all the numbers over and over and over, which I personally don't recommend because it's real easy. Look at all these zeros that are in here. Let me make this real big. It's real easy to miss one of those zeros, so be very careful if you're doing it this way. It's not wrong. Like, obviously, Samita's doing it, so it works. And Samita knows exactly what she's doing. But if this were me, I would lose one of those zeros. That's something that I would do. And it's super easy to do that, so just be very careful. All right, so that was the first one. I gotta go back to the chat to see what we were doing here. So that was 6. So William also wanted to see number 8, so I gotta find that. So number 8. Oops, sorry. Hold on. It's in where this is in a different spot on my screen than it is on yours. All right. So element X has 2 naturally occurring isotopes with relative atomic masses being 56.902 and 58.022. The average atomic mass of the element is 57.783. Calculate the percent abundance. So we have done this exact thing, so I don't have to do the algebra again. All the algebra is all set, except I do need to renumber what these are. So we can do this really quickly. So we'll just get oops, I need the eraser. We'll just do this. We'll do the exact same thing because it's the same problem, right? So I'm going to call the first one 57. So we'll say 57. I'm going to do a fancy X because I don't want it to look like variable. And this one will be 58X. And then I got to fix the average here. So you can kind of use it as a formula. So whatever that is, so this will be 57, 58. And there you go. So it's kind of like a formula, but it really depends on how you define your variables. Since the algebra is not that hard, I do it from scratch every time myself. But here we already have it on the screen, so I will use it if it's available. Okay, so all these 12s become 57. So anywhere I see a 12, I'm just going to write 57. So 57. And then anywhere I see a 13, I'm going to write 58. So you, and you, and you, and you, and you. Because you can see this is almost more confusing than just starting the problem over from scratch and doing it again. Oops, I gotta fix these. So 58, 57. And now I'm writing 85 for some reason. And then we don't need any of this over here, so we could just erase this part. Oops. That didn't work. Boop, it's gone. We can get rid of that too. All right, so we did the exact same process because it's the same problem. If you are asked to solve for the percentages, you're going to do this sort of process. So let's scroll down here. And we'll just plug in all the numbers. So the average mass for this isotope. Can you use Wolfram Alpha? Oh yeah, we totally could use a Wolfram Alpha. So you could type the expression into Wolfram Alpha. Once you get to this that I'm going to write right here, you could put this into Wolfram Alpha. So that would be, the average was 57.783 mu. The larger isotope was 58.022. The smaller isotope was 56.902. And the larger isotope was 58.022. So all these digits are going to go to the thousands place. It looks like. So thousands and thousands. So really what you're going to have to do is check for sig figs here. So 57.783 minus 58.022. I believe you're going to have 3 sig figs when you do that subtraction. Yeah. So the top number became this. And the bottom number, I was going to do this on Wolfram Alpha, but it turned out that it was already half in my calculator. Those cancel out, and these cancel out. And this is still X. This should be a plus, sorry. And that's what I got. So you can sort of use this as a formula. However, the big issue that you have to worry about is getting these things mixed up. Because if you flip any two on accident, you get the wrong answer, obviously, right? So I prefer not to commit formulas to memory that I can derive, because I'm an old model and I only have so much memory. Like, I'm basically obsolete. My brain is obsolete, right? You guys have the newer version of brain. So if you want to remember a bunch of formulas, go right ahead, right? But it's too hard for me. So I derive every time. I feel like that's easier. But as far as the Wolfram Alpha is concerned, absolutely use it as much as you can, because you want to save time. You don't want to do all this math, right? Like, I'm not testing you on math. So if x is this, then y, which is 1 minus x, is 1 minus that number. 0.787. And so x, which was the smaller isotope that I called this, and then y, which was the larger isotope, was that. So that's what I got for my answer. And we can check what Samita got. That's the wrong worksheet. Alright, and that's what she got. So we were pretty close. Now, the difference in sig figs could come from me choosing a different variable for x. So if I go and look at what she did, she probably called the other one x, Or she solved for y. Yeah, she well, what is she doing here? That gives her a different number of sig figs. Oh, no, she just made a mistake. That's all. So she did what we did and then wrote down 4 digits. So there should only be 3. Okay, what's the next problem? So that was unit 6 and 8. So now I have 16. So that's on this worksheet. Number 10. I actually really like this problem, and I wish I had thought of it for like a quiz question or something. But this is way harder than anything you do on the quiz. So first of all, is this a dilution? What is a dilution? What's the definition of a dilution? Like, obviously, you can see the word no. It's not a dilution. Oops, I didn't mean to make it blue. So a dilution is when you add what to your solution? Yeah, it's just water, right? So when you add water to a solution, you're diluting it. But if you add another acid, you're not diluting it. You are adding more acid, right? So you cannot use... Oops, that's not the writing cursor. Can't use the dilution formula for this problem. Canvas is up. Oh, that's exciting. Let me click on this and see how long it takes to load. Hey, everything loaded really quickly. That's good. Okay. Hooray! You can take the final exam. Oh, I know that's kind of a bummer, but all right. So to solve this problem, first we need to draw. First, I'm going to draw a picture so we can explain it. So here's flask A, and flask A has 150 milliliters of 0.250 molar HCl. And so what that means is that I'm going to have some amount of HCl in here. And we count the HCl in moles, right? So I'll write that. And I'm going to pour this into another flask, which is even bigger. I don't know what's going on over here, but this flask has 450 milliliters of 0.374 molar HCl. So it's bigger and it has a higher concentration of dots in there. So I got to put the dots just a little closer together. So in both of these cases, there's HCl in there, right? Well, what would the molarity of the total solution be? Well, what's the definition of molarity? It would be moles total divided by volume total. So what we need to do is we need to figure out the number of moles total for both the solutions and then just add them together, right? And then for volume total, we would just add these two numbers together. So 150 plus 450. So the total volume is pretty trivial. I'm adding the dot in there because otherwise we end up with two sig figs, and that seems weird to me. So, also, there might be a dot, and I can't actually see it because it's real tiny on my screen. So, there's the total volume. Let's figure out the total moles. So, I'm going to call this mole 1, and I'm going to call this mole 2. And then mole 1 plus mole 2 should be mole total. I don't know how I got there, but I got there. Mole total. So that's not too bad. So let's do that. So the molarity of this solution was 0.250. I gotta write out all the units here, though. And the volume was 150 milliliters, so I gotta turn that into liters, yeah? So that I can do that. So there's mole 1. We'll do the same thing over here, so 0.374 times the volume and I got 0.1683. Well, I only get to keep 3 sig figs. And then I'm just going to add those numbers together. And so that would give me that many total moles. And then the molarity of the new solution would just be that many total moles divided by the total volume. So we'll just do that. So the molarity of the new solution is the total moles over the volume total. It's got to be in liters because that's how we do molarity, right? And so the result that we get is 0.343333 forever. There you go. So if you're ever given this type of problem, which you won't see this on the exam because I don't have a problem this challenging. Remember that you can go back to just the basic definitions. Like, what is molarity? How do you calculate it? Well, it's moles over liters. Okay. All right. How many moles are there? Well, this solution has this many moles, and this solution is that many moles. And you could sort of rationalize out any problem that I give you by going back to the basic definition. And that's why I always start doing these problems by writing down stuff like this. And you've probably seen me write this formula like 75,000 fucking times, right? Like, all I do is write the formula for molarity. I just write it over and over and over again. And the reason for that is because write down the most basic stuff that you know. Not because you need to remind yourself, but because it's easier to see it once it's written down, right? So you can everybody here knows that molarity is moles over liters, right? But you might not think of it, and then you'll be like, "Oh, duh! It's so obvious." So just write down everything that you know for a given problem, no matter how elementary it seems, because you might use it. That's not just a teaching strategy. That's not why I'm doing it. I do that for me because I can see things better than I can visualize them, I guess, and most people can too, I suspect. Just a little insight into the brain of Professor Wes, I guess. I don't know. What else do we got here? So we got that was Unit 16, number 10, and then I have. Oh, I should check Samita's answer. She got 0.343. It looks like it sort of scrolled off the page, but so she got the same thing that we did. Okay, so now I have Unit 10. What question was that? 1D. That's H. Where is D? Oh, duh, if I just keep scrolling. Like, why is it H? Because they're lettered top to bottom. All right. Draw the Lewis structure for this. Hey, remember Lewis structures? That was so long ago, right? Yes, there will be Lewis structures on the exam. All right. So draw the Lewis structure for C2H4. Remember the 5-step plan? Remember that from forever ago? What was that 5-step plan? Do you guys remember? Because I sure don't. There were 5 steps. Can someone type them out in the chat? I gotta make you guys do something, right? Like, of course I know the 5 steps, but do you guys remember them? And if you don't, they're in your notes, so you could just type from your notes. That's fine. Yeah, go ahead and type in the steps. As many of them as you can remember. So there's the first step. Count the electrons. Not all electrons, though. Which ones? Draw the framework is step 2. Very good. Yeah, valence electrons. Those are the ones that we want. So I'm going to write these down as we come up with them. So count valence electrons. All right, what's next? Place electrons one at a time by rotating around it. So that's I understand what you're trying to say there. So outer atom octets is what I would have used. All right, we got step 3. What was step 4? This is good. Keep going. You guys are doing all right. Leftovers on central atom. All right. And then at the very end, we've run out of electrons and everything doesn't have an octet yet. What is our last resort here? We have to do multiple something. Multiple bonds. Yeah. Good job. All right, so let's do that. So we're going to do these one step at a time. So step 1, count valence electrons. So each carbon gives you 4 because it's in group 14. And each hydrogen gives you 1 because it's in group 1. So this should be 12. So our molecule should have 12 electrons total in it. So let's draw the framework. Now, sometimes it is a little bit challenging to figure out what the framework's supposed to look like, particularly if you have multiple of the central atom. My suggestion is that if you are given 2 of the central atom, connect them together and then make the molecule as symmetrical as possible. So this is what you should end up with, is something like this, because it's as symmetrical as possible. Now you might think, oh, what if I just put 3 of them over here, and I did this? Then what will happen is you're going to have a hard time making an octet around everything, and using up all the paired electrons. So symmetry in our molecules for these, because we're working with simple molecules. So there's our framework, and then we're going to connect everything together. 2, 4, 6, 8, 10. So we only have 2 left. So we've done our framework. Our outer atoms are hydrogen, so they don't need octets. We have to put the leftovers on the central atom. Well, you pick either one. You could do this. So we've done that, but not everything has an octet if we do that. So this is where we get to at the end of step 4. So we need to make multiple bonds. So there's only one way to do that, and that's to do this. So we take those electrons, we throw them in a double bond. And now everything has an octet. Now, this is the correct structure. Let's see what would have happened if we had done it the other way, where we did a framework like this. So we'll do something like that, right? So there were 10 of my electrons, so I started with 12. I used up 10. I got to put the last 2 on an outer atom. And so there's all 12 of my electrons. And now I don't have octets everywhere, and so my next move would be to make double bonds somewhere. And you might think, well, what if I just do this? And that's great and all because it gets you closer to an octet, but now you've broken the octet rule. Octet rule. And so this is no good. Also, this guy doesn't have an octet either. And there's no more electrons to share, right? So this direction that we went, where we tried to do 3 on one side and 1 on the other, just didn't work out. And it turns out that with Lewis structures, 99% of the time, if you set it up incorrectly, you'll get something that doesn't follow the octet rule and looks weird and confusing, and there's a reason for it. It's because it's wrong. So the top structure looks great. It looks symmetrical and everything. And in nature, it turns out symmetry is a thing that occurs all the time. Not because of any design, but because it's just the simplest and lowest energy structure that is possible. Nature is incredibly lazy, by the way. I don't know if you've met nature, but nature just wants to do the easiest thing all the time. All right, so that's that problem, and I think we are due for a break. So I do have other problems. Where'd my cursor go? There it is. Sorry, I'm just checking here. So I did that, and then there was a. So, William, you asked this question. Are you referring to the lab? Because I wasn't sure. Worksheet analysis question 21. Let me know. We're gonna take a break, and if it is the lab, I'll just get the lab on screen during the break. So, we'll do this. We'll get that up. Yeah, it was the lab. Okay, cool. I'll go find that. And we'll start the timer here, and we'll just... You have to listen to 10 more minutes of the Nintendo Wii Shop, so I'm sorry. Not sorry. Hi, sorry about that. Let me turn this down real quick. I was answering questions with another student here, and we were in the middle of the conversation. Like, I can't just stop here. So, okay. So, that was the thing I was looking at. Another question that came up was this one right here. For a separate titration, this one using phosphoric acid and sodium hydroxide, because sodium hydroxide is such a good titrant. It's just cheap and abundant. So you see it in all these equations here. So we're going to react sodium hydroxide with phosphoric acid. So we do need a balanced chemical equation first. All right. Now, you make two products here, right? Now, based on what you've seen in the lab so far, you should be able to predict the two products. At the very least, you should definitely know what one of them is. What's the first product? What's the product of any acid-base reaction if the base is a hydroxide? What did we say it was? H2O. Very good. So we're going to make an H2O. And we're going to make something else. What is that something else? What's whatever else is left in the substance, right? So it's going to contain sodiums and phosphates. And we know what these ions are. We just need to put them together to make the right formula, right? So I need 3 positives to balance out the 3 negatives. So I'm going to need 3 of these to get this. Now, if I need three sodiums, I got to put a 3 here. And there you go. That ends up being the balanced equation. So we have not done this. This is sort of a critical thinking exercise of like, okay, I've seen these equations. Can I get to the correct answer? The other thing you can do is just look it up. What is the reaction of sodium hydroxide and phosphoric acid? And you'll find this equation. So we're going to talk about how to deduce these sorts of equations and write out net ionic equations, stuff like that. We're going to do that in 161. A little beyond the scope of this class. But since I'm giving you like a week and a half to basically, with the internet available, you could look it up. That's fine. So that's the harder part of the problem to do. This part where we're doing the calculation is pretty straightforward because it's basically the experiment that you just did. So we are putting 0.1350 molar NaOH in the burette. So we're going to have this. I've already forgotten the number. 1350. So that's my molarity. I don't know what the volume is. We're going to solve for that because what volume of NaOH is required? And over here for phosphoric acid, I have 10 milliliters. And the molarity is 0.06550. All right. One of these I know the number of moles to, and it's the one that I have both numbers for, right? Because if I write down m times v, I get moles. So that means that I know the number of moles of phosphoric acid here. That's known because that's going to be this right here. And then using the balanced chemical equation, I can turn that into moles of NaOH. And then I can turn that into a volume of NaOH and answer the question. So now we've done that, I want you to try to solve the problem. I'll give you like 5 minutes to do the calculation. And then I'll go over the answer. We'll treat it like a practice problem, like we were in class again. You know, for the last time. Because after today, you won't hear my voice anymore, right? Oh, Professor West, I miss your class. Your voice brings me comfort in chemistry. Well, if you're taking 163 in the spring, which you're not, because you take 162 at some point. You can see me. Well, you can see me on campus. I'll be on campus in the spring. I hope. That's my hope, anyway. Who knows, right? Go ahead and try and do this problem. I'll shut up. I'm going to hit mute and just talk to myself. See you in a bit. All right, there's some answers coming in, so we'll do 1 more minute, and we'll go over the answers. Make sure you're turning that volume into liters. All right, let's go over the answer here. So, I need to know the number of moles of phosphoric acid. So that's going to be the molarity, which was this, times the volume, which is 10 milliliters. I got to turn that into liters here so that these cancel out. So I have 0.06550 times 0.01. And I get 6.550 times 10 to the minus 4. So that's the number of moles of phosphoric acid. Now we can turn that into moles of sodium hydroxide. By doing the stoichiometry. So moles, phosphoric acid, moles NaOH. So those cancel out. And we need to go to the balanced chemical equation. So if you remember from above, for every 1 phosphoric acid, there were 3 sodium hydroxide. So those are up here. So there's my 1. There's my 3. Oops. We could drag this down here. So we'll do that. And so that will tell me the number of moles of sodium hydroxide. When I do that, I get 1.965 times 10 to the minus 3. Or we can go back to decimals here. 0.01965. So there's my moles. And I got to convert it to a volume, right? So if I multiply by the molarity, and the molarity of sodium hydroxide was right here, but I have the molarity upside down, so 0.1350. So moles sodium hydroxide per liter. So if I do that, I will get 0.01456 liters. And then I can convert this to milliliters by just moving the dot over 3 times. So and I should get this. So what it looks like is that you may not have used the correct unit at the start. If you got 14.56 liters, you might have put in the volume in milliliters. You have the right number for liters, but it was labeled milliliters. So be real careful, because Canvas will look at that and be like, oh, that's not the right answer. And you get no credit. So again, write out all your units every time. So when you're writing out all of this stuff here, like right here, write all these units out. I don't do it because it's like good for you to see it necessarily. Like it is, but my intent is that I do it every time because I don't want to end up at the end and be like, oh, what does this number mean? I don't know what these units are. So always write out your units. I know as students you're like, oh, I just want to write the numbers. The numbers are the only important thing. No, the units are more important than the numbers, because if you have the wrong unit, the number is useless, right? If you went into the lab and used 145.6 liters to do this reaction, you'd use up all the sodium hydroxide in the building, which is a lot, right? So, so that number doesn't help you if you're using that much. Likewise, if you only added 0.01456 milliliters, the reaction would not be actually done. Okay, that's all the questions I had. So if there aren't any more questions, we're going to do last call for questions. While I'm waiting for questions, let me read the email I got from Hannah. Hannah is our Canvas specialist, basically. Like, all the Canvas stuff goes through her and then goes to the rest of us. She's just like the Canvas like overlord, we'll call it. Like, she knows everything about the system and makes it work for all of us. So Hannah said that I guess I was right. It was part of the Amazon Web Services issue. This, you might have received this email because it was sent all campus. Currently, as of 3 p.m., EVCC's Canvas system appears to be back up. It's moving very slowly, like commuter traffic at rush hour. Our guesses in structure, which is the people who made Canvas, are working on opening up more data. So please be patient. If you're having trouble logging in, try and use a connected, like wired, connection. So like a laptop or desktop computer that isn't using broadband Wi-Fi. That will probably be fastest. Wi-Fi on a laptop would be the second best option. The worst option would be using your mobile device to use Canvas. Just don't. Like, you could view stuff in Canvas, but don't submit stuff through it. It's not advised. Use Chrome or Firefox. Those are the supported browsers. And use the link on the EVCC page to get to Canvas, just in case your links are not working or whatever. If you're having trouble getting onto Canvas later tonight, let me know. And if you want to email me from a different account to request an exam to be moved to Thursday, that's fine. I just need your full name and what section you're in so I can find you. Otherwise, you'll get an email back that says, "Hey, who are you?" Which happens sometimes. What about an iPad? I can't speak for an iPad because I don't use any Apple products. In theory, it should work. I don't see why it wouldn't work. But if it's not working, try a Windows-based device and see if that is working. I think Hannah wrote that just because, like, that's what the documentation says for Canvas, which is just, hey, this is supported on these platforms or whatever. All right. Any other questions? Go ahead and put them in the chat. Otherwise, we're going to wind this down in about 5 minutes. So I'm going to hit mute, and we'll just hang out for a bit. I'm just looking for that problem. Oops, that's not what I meant to do. 25? Oh, right, it doesn't match. This is right here. This is the middle of my screen because I have it truncated in a weird spot. Oops, there we go. All right. So I gotta cover up Samita's stuff here just so that we do that. But sure, we could do that. Let me scroll all the way up to the top. Okay. Pen. There we go. Okay. So let me see. 8.63 is that? I can't read that number. Is that times 10 to the 6 or 10 to the 8? 10 to the 8. Okay. And then that's micrograms per cubic millimeter. And so we want pounds per gallon out of this. So we need to do a bunch of crazy stuff with our number. So micrograms, we can get to pounds by doing something like this. So that doesn't really look like micro. Erase. So micrograms can be turned into regular grams, which we can turn into pounds. That's easy enough. So let's start there. So microgram to grams, and then grams to pounds. So how many micrograms, or how many grams are in a microgram? So 1 microgram, micro was 10 to the minus 6, yeah? And then how many grams are in a pound? Well, you can look that up on Google. So this would be how many pounds there are in a cubic millimeter. But we don't want a cubic millimeter, right? We want a gallon. So we need to convert away from this. And this is kind of an obnoxious unit to be given. Because if we had cubic centimeters, that's milliliters, right? So we had to do something like this so that we can go back to that. So that we can go to this. So that we can go to that. So that we can go to gallons. That's the most direct route I can think of without like using Google for something. So let's do that. So we'll do this, which I have to cube. How many meters are in a millimeter? 10 to the minus 3. And then we got to cube all of that. So this will cancel out with that. Then I got to turn that into centimeters, which I'm going to start down here on this next line. So meters to centimeters cubed. And then 1 centimeter is 10 to the minus 2 meters. We'll cancel out our units. And then a cubic centimeter is the same as a milliliter. So now we got milliliters. We turn this into liters. And then liters into gallons. That one I had to actually look up. So let's look. So 1 gallon to liters. I got 3.785. Make sure you're using US liquid gallons. There you go. I have messages in the Discord. I'm just checking something. Okay. Just checking that it's not. The stream went down. All right, so I have all these numbers now. I'm going to multiply all the numbers on the top divided by all the numbers on the bottom. Where's my phone? There, or not phone, but calculator. So 8.63 times 10 to the 8 times 1 times 10 to the minus 6 times 1 cubed times 10 to the minus 2 cubed times 1 times 3.785. And all of that will be divided by 1 times 453.6 times 10 to the negative 3 cubed times 1 times 10 to the minus 3 times 1. And when I did all that, I got 7,201,000, something like that. Oops, what did I just do? That's not the pen, that's the ink dropper. So I got 1, 2, 3, 4, 5, 6, 7.20 times 10 to the 6, yeah. So in a gallon jug, there are 7.2 million pounds. So obviously that's not possible. That is the number that Samita got up there. So we did the problem correctly. This would be like a gallon of neutron star. Or something like that. Samita went shopping at the neutron star shop again. I bet Christine in physics encouraged her to go. They're having a sale at the neutron star shop. Ooh, I'd always wanted a gallon of that for a chemistry problem. But yeah, if you're looking at that number and you're like, that's way too fucking big, there's no way, then yeah, you're absolutely right. Like that is too large of a number. But it's impossible to tell really from like this many micrograms per cubic millimeter. So obviously this problem, well, obviously for me, this problem was written with just like, hey, here's this awful unit, turn it into this other awful unit, and then I'll just pick a random number. And it doesn't have to contextually make sense, since the exercise is doing all the conversions. But it does annoy us as people doing the problem, in the sense that, like, how do you know that your answer is correct? Well, you kind of can't, right? If you write out all your units and you look at it, you could be confident that, yeah, I canceled out everything. And I got to the target units, which were pounds. Where'd my pen go? There it is. It's the wrong end of the pen. Every time I pick up the pen, I pick up the wrong end. So there are my units. Those are the only units that are left over, so they're the units of the answer. Right? Nothing will go horribly wrong. It's just neutron star. Neutrons are everywhere. They're really cheap. Can you explain lab worksheet number 2? Can you be more specific? Do you mean like actual worksheet number 2? Like the one that we did months ago? Or do you mean lab worksheet, the lab worksheet that's due this week and problem number 2? Because I'm assuming you mean worksheet number 5, but I do want to make sure. I need to know where problem 2 is. Where is it? Okay, yeah, that's what I thought. Alright, I do want to look through the lab really quickly. So, do we talk about this? in this experiment specifically. So this is more of a... So question number 2, let me put it in the box again. Question number 2 kind of uses your information from previous labs about, like, what should you be using glassware for? And this question, this is kind of a legacy question, unfortunately, from the before time when we were actually allowed into the lab. And so it's so much easier to answer this if you've actually seen and used the glassware, which obviously we haven't because we're not able to go into the lab. So let me just write some stuff down here for you. So a beaker. So you probably know what a beaker looks like. It looks kind of like this. But the little marks on these are really, 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 really crude. So, like, if you had a volume like, say, this, and you had to measure it, well, you get, like, 2 sig figs out of it, so... Which is not very good, right? So beakers are crappy for precision because they don't have enough sig figs. And yeah, your answer is pretty much exactly what I'm looking for, I think. So beakers are crappy. Graduated cylinders are just really tall beakers. I'm trying to, like, draw it correctly, but, like, really, who cares, right? And so these have marks that are much closer together. So if your liquid falls in that, and your marks are like this, so this is, I don't know, 12 and then 13, and then each of these dots is 0.1, you could get something out of here that'd be like, okay, well, it's between 12.4 and 12.5, so I could say something like that. So this is a graduated cylinder. Oh, what'd I do? I clicked up. Oh, no, that's not at all what I want. I want that. No, that's not all. Oh, I, like, pulled it out of the screen somehow. Sorry, I'm trying to fix it. How do I get this back on? Oh no, what have I done? So I know how to fix this. Hold on. So select all. Copy. Oh, I can just save it. We'll just save the file. And then open. There we go. I accidentally, like, drug it off of the screen, and it became its own window, and then OBS stopped capturing it. So that was no good. All right, so I have a graduated cylinder here, which is better. And then the other pieces of glassware are just many more sig figs. So a pipette looks like this. And there's a line on it. And it usually gives you something like this or this. And so you get a lot of sig figs with those. So, and then a burette is the same. Burettes are the things that drip down like that. And you have the little stopper right there. And then you have lots of lines. And the lines are every 0.1 milliliter, so you can guess the next digit. So that's a pipette, this is a burette. And a volumetric flask just holds a fixed amount to a high number of sig figs. So the gist of that question is, if you don't need a lot of sig figs, use a beaker. If you do need a lot of sig figs, use a pipette or a flask. And yeah, that question was something that I would always ask when we were in person, and everybody always got it because I am harping all quarter long when we're in the lab. Are you using a beaker to measure something? Or like, well, no, because I can't get enough digits out of it. Like, yeah, of course not, right? So beakers are shit for sig figs. So you use beakers to carry things. That's really what a beaker's for. Is you can't use it to carry stuff. Don't measure with a beaker. Just carry with a beaker. Same for an Erlenmeyer flask. Don't measure with those. Just carry stuff with them. That's one of the things that's real hard to teach in this class when we're all online, is because, like, if you don't see the glassware, you don't get to see the lines on it. Yeah, there you go. That's kind of my hope, I guess, is that if you aren't sure, you can look up pictures of stuff. So you can look online anywhere, and you can find pictures of beakers, right? Like, beakers are not a novel thing that only Everett Community College has access to. But there are a bunch of different beakers out there and a bunch of different graduated cylinders, and so there is some variance in what you might find. And so there would be some variance in your answer. But that's basically what I'm expecting for that problem. There's another question at the end. I think it's question 20, which is, which solution is appropriate? Should you use 0.2 or 0.20000 for working this demo here? Let's put that on the screen real quick. It's sort of the opposite of this question. Instead of which glassware should you use, it's which one of these should you make. And again, it has to do with sig figs and like what the purpose is. Are you collecting data for this? Like, if you need numbers, having a 1 sig fig solution is kind of lame, right? Like, all your answers would have 1 sig fig. So, but if you're just doing a demonstration for kids, do you need to have that many digits? Do they care? What does the reaction of zinc with acids look like? That's probably on YouTube. You could probably look up a video of that. So, with all of that information put together, which solution's more appropriate to prepare? Because one of those takes a lot longer to make than the other, right? The more precision there is, the more time is required to make sure you're correct. Whereas with 1 sig fig, you just whip that together almost instantly, right? That's kind of a story that I have when I was preparing to do lab tech stuff for the college. There was a time where I was the lab tech at Everett Community College because our lab tech had to take personal leave for something happened. And so I was the lab tech and the instructor for about a month and a half, I want to say. And I had to make a solution of 1 molar H2SO4, which just with 1 sig fig. And I was like, well, okay, I'll just pour bloop, there you go, it's done. You just have to get close, right? Because it has to round up to 1. And the other faculty were like, I never really thought of it that way. Like, yeah, if there's only 1 sig fig, I just got to get close, right? So I could do it in 20 seconds. If you need 1.000 molar HCl, though, that I have to actually go out and measure. Like, I can't just estimate that. So, just some stuff that you can think about with what the numbers mean. So if you said 0.200 was better because it's more accurate, do you actually need the accuracy, though? Read the question carefully and determine whether we need to make the 0.2 molar solution or the 0.200 solution. Because it's which is most appropriate, not which is better. which is more appropriate? Like, I could wear a tuxedo and tie to teach every day, or I could wear a shirt and slacks. Which one's more appropriate? Should I wear my finest clothes to teach? Like, wouldn't that be kind of weird, right? Like, surely the suit is better, but is it appropriate? So be careful what the word means, too. I'm going to leave that one for you guys to think about, though. Hopefully I haven't muddled that up. Oops, I clicked on the wrong thing there. There we go. Okay, so I guess that's it, because we are out of time. I'm happy we used all the time, though. That's great. I always worry about these, because when I do these review sessions, I'm always like, oh, nobody comes to them. I'm not going to have any questions. But we used all the time, so that's really good. So I hope that was helpful to see. And yeah, our labs are actually pretty good at our campus. So hopefully you'll get to see them at some point. I hope we get to go back soon. I know some labs are in person next quarter. We'll see if Omicron changes that, though. I do want to thank everybody for coming out to the lecture and for being a part of Chem 140. We did the whole sad, like, oh, thing last week where I, like, surprised this was hidden in the back the whole time. But I don't want to do sad goodbyes, so we'll just play this and call it a night. Best of luck on your finals. Good luck in Chem 161. Hope to see you on campus, too.